Hey everyone, and welcome back to another deep dive on the Explainer. Today, we are literally tearing down the walls. We're looking past the concrete and the steel to examine the invisible, foundational forces that are basically holding our physical world together. Honestly, it's like a giant puzzle. We are talking about the microscopic battles happening inside the very beams right above your head.
Think about this for a sec. Have you ever driven over a massive suspension bridge, or maybe stood under the cavernous ceiling of a skyscraper, and just thought to yourself, how do engineers know exactly how many nails, or bolts, or welds it takes to stop this whole thing from just completely structurally failing? Well, the answer definitely isn't guesswork. It lies in the absolutely fascinating physics of how forces actually move through materials.
Okay, let's dive into this. Here is our roadmap so you know exactly how we're going to tackle the math today. First up, the built-up beam problem. Number 2, understanding shear flow. Third, surfaces of resistance. Fourth, our first case study, the T-beam. And finally, case study number 2, the box beam.
All right, so let's kick things off with Section 1, the built-up beam problem, and exactly why things want to fall apart in the first place. So, when engineers need to achieve greater load resistance for really large structures, they can't always just go out and find a massive solid piece of wood or steel. Building bigger introduces some incredibly unique mechanical challenges. Because of that, members are built up from several composite parts. But I want you to imagine bending a standard deck of playing cards in your hands. As you bend the deck, you see the individual cards easily slide right past each other, right? Well, the exact same thing happens when you stack structural materials and put heavy weight on them. To keep these composite parts from sliding relative to one another, we absolutely must introduce fasteners, things like nails, bolts, welding materials, or industrial glue. You can see in the diagrams how multiple separate pieces get joined into these really complex I-beams or hollow box frames. But the ultimate engineering question is this: precisely how strong do those fasteners actually need to be?
Moving right along to Section 2, understanding shear flow. This is the glue of the math world.
This is where we transition from that physical, real-world construction problem to the really elegant mathematical tool that engineers use to actually solve it. Because before we can pick the right bolt or figure out the spacing for our nails, we need a highly specific, measurable metric. Enter shear flow. In engineering, this is typically denoted by the lowercase letter q. To design our fasteners safely, we define shear flow as the shear force that must be resisted by the fastener, specifically measured as a force per unit length of the beam. Think of it quite literally as a physical force flowing down the horizontal length of the beam. Now, what's really interesting about this slide is the visual breakdown, where you can actually see this invisible flow in action. The core formula we use is Q equals V times Q divided by I. If you look at that beautiful 3D cutaway on the left, V is the internal shear force pushing vertically. I is the moment of inertia, which is basically the beam's overall resistance to bending based entirely on its shape. And Q is the statical moment of area. That essentially represents the specific piece of the beam that is desperately trying to slide away. I know, it looks like alphabet soup right now, but it's actually an incredibly logical system to track exactly where the stress is concentrating.
And honestly, don't panic about the math, because no matter how complex the structure looks, we always follow this super simple 3-step mental framework. Step 1, find the internal loads. That just means figuring out the raw force hitting the structure. Step 2, calculate section properties, which is defining the physical geometry of the beam itself. And Step 3, apply that shear flow formula we just talked about. If you follow these 3 steps in order, the math practically solves itself.
Which brings us to Section 3, surfaces of resistance. This is where the battle truly happens.
You see, the specific geometry of your beam completely dictates how structural force gets distributed across your fasteners. Take a look at these 3 cross-sections. Do you see those bold red lines? Those represent the shear planes. They are the exact physical borders where the blue shaded parts really want to slide past the gray parts. Now on the left, we have a simple T-shape with just one surface of resistance. That single row of nails has to take 100% of the shear flow. But in the middle, the flow is neatly split across 2 surfaces. And on the right, it's resisted at 3 distinct surfaces. Every single time you add a surface of resistance, you are physically dividing the flow that the fasteners have to fight back against, severely easing the burden on any one single point.
All right, Section 4, Case Study the T-beam. Time to put the theory to the test.
We've got our 3-step framework, we've got our formula, so let's put it all to work. Here is our mystery to be solved today. We're looking at a simple beam built from 2 boards forming a T-shape. The diameter of the nail connecting them is exactly 3 millimeters, and those nails are placed precisely 200 millimeters apart along the entire span of the beam. So, based on the downward loads you see pushing on this beam from above, we need to mathematically figure out the absolute maximum shear force trapped inside just one of those nails.
Following our trusty framework, we kick off with step 1, internal loads. Looking at that red shear diagram mapped right beneath the beam, we can easily spot that the internal shear force, RV, peaks at exactly 600 newtons over on the far right side. Okay, step 2 is calculating our section properties. By mapping out the neutral axis and running our geometric calculations for that T-shape, we find our moment of inertia, I, is 5.333 times 10 to the negative 6 meters to the fourth. I know, those units sound totally wild, but this number simply gives us the unique structural fingerprint of our beam.
So, the crucial point is right here in step 3. This is where we bring the whole shebang together by plugging our values into the formula, V times Q over I. First, we calculate the shear flow pushing through the neck of the beam. Then, we isolate a single fastener by multiplying that flow by our exact nail spacing, which was 200 millimeters. Through this, we discover that the specific sliding force attacking a single nail is precisely 1,350 newtons.
But stop and think about that. What does a horizontal slicing force of 1,350 newtons actually do to a tiny little 3 millimeter diameter nail? Well, when we divide that force by the tiny cross-sectional area of the metal nail itself, we reveal our final answer, an astounding 191 megapascals. That is a massive, highly concentrated shear stress isolated on one single tiny peg. Literally, if the steel in your nail isn't rated to handle 191 megapascals, your beam breaks and the whole structure fails. No way around it.
Let's up the ante in section 5, case study the box beam. Okay, we are upping the stakes considerably here. We're now looking at a much more complex, hollow structure, and this time we are working backward to determine the actual nail spacing based on a strict physical force limit. Here's the setup for example 2. We have a hollow box beam constructed from 4 individual boards nailed together just like you see here. The entire beam is subjected to a vertical downward force of 300 newtons, but here is the major constraint. The hardware store specs state that each nail can only safely support a maximum shear force of 200 newtons. So we have to determine the required spacing of the nails at 2 totally different junctions, point B on the inner web and point C up on the top flange, so that the beam will safely support the load.
As always, we hit step 2 of our framework, section properties. And I love this part, because for a symmetrical hollow shape like a box beam, calculating the moment of inertia, I, is wonderfully simple. You just calculate the I for the solid outer rectangle, which is 1/12 base times height cubed, and then you simply subtract the I of the empty inner rectangle. It's just a beautifully elegant bit of math. It gives us an overall section property of 46.28 times 10 to the negative 6 meters to the fourth.
Now we calculate our required spacing using that strict 200 Newton limit per nail. And this brilliantly illustrates how calculating at different junction points changes the engineering entirely. On the left, we look at point B, which is pinning the sideboard. The specific piece trying to slide away here gives us a particular Q value, leading to a calculated maximum spacing of 0.198 meters. But look over at the calculation for point C on the right. Point C pins the top board. Because it has a totally different area trying to slide away, the mathematical flow is weaker, and the required nail spacing widens out to 0.316 meters.
So let's summarize exactly what these findings dictate for a builder out there on the ground. Because point B experiences highly concentrated shear flow, you absolutely must design for a tighter nail spacing, meaning using a nail every 200 millimeters. But up at point C, the stress is distributed differently. This means you can safely save materials and labor by spacing those nails 300 millimeters apart. The exact geometric placement entirely dictates the required density of your hardware.
We have looked at some intense math today, the formulas, and the microscopic forces acting constantly inside seemingly simple wooden boards. Which leaves us with a rather profound final thought. If a single millimeter of miscalculation in area, or a slight misjudgment in shear flow, changes absolutely everything about how stress attacks a simple joint, just how perfectly secure are the massive, towering structures we confidently walk into every single day? It is certainly something to appreciate the next time you drive across a bridge. Thank you so much for tuning into this explainer, and keep learning.